Circular motion, exercise question 22, from H.C. Verma. Here is the S-shaped track. The first arc, ABC, is a convex bump. Point B is at the top of the bump. The second arc, CDE, is a concave dip. Point D is at the bottom of the dip. The two arcs join smoothly at point C, where the road makes 45 degrees with the horizontal. At B, the normal force pushes up while gravity pulls down. At D, the normal force pushes up and must exceed gravity to provide centripetal force. A cycle with its rider, total mass 100 kilograms, travels at constant speed 18 kilometers per hour. The question says, a track consists of two circular parts, ABC, which is a convex bump, and CDE, a concave dip, of equal radius 100 meters, joined smoothly at C. Each part subtends a right angle at its center. A cycle weighing 100 kilograms together with the rider travels at a constant speed of 18 kilometers per hour on the track. Find, Part A, the normal contact force by the road on the cycle at B and D. Part B, the frictional force on the cycle at B, C, and D. Part C, the normal force on the cycle just before and just after it passes C. Part D, the minimum friction coefficient for the cycle to travel at constant speed. Take G equals 10 meters per second squared. The key concepts. On a convex surface, at the topmost point, the weight mg minus the normal force n provides the centripetal force, mv squared over r. So the normal force is less than the weight. On a concave surface, at the bottommost point, the normal force minus mg provides the centripetal force. So the normal force is greater than the weight. At any inclined point making angle theta with the horizontal, we resolve mg into radial and tangential components. The radial component is mg cos theta, and the tangential component is mg sin theta. Friction must balance the tangential component for constant speed. Let us first note the given data. Mass m is 100 kilograms. Radius r is 100 meters. G is 10 meters per second squared. Speed is 18 kilometers per hour, which converts to 5 meters per second. So mg equals 1000 newtons. And mv squared over r equals 100 times 25 over 100, which is 25 newtons. Part A. At point B, the top of the convex bump, the road is horizontal. The weight acts downward and normal force acts upward. The net inward force, mg minus n, provides the centripetal force mv squared over r. So n at B equals mg minus mv squared over r, that is 1000 minus 25, giving us 975 newtons. At point D, the bottom of the concave dip, the road is again horizontal. Now the normal force acts upward and weight acts downward. N minus mg provides the centripetal force directed upward toward the center. So N at D equals mg plus mv squared over r, that is 1000 plus 25, giving us 1025 newtons. Part B, friction. At points B and D, the road is horizontal. There is no tangential component of gravity along the road surface. Since the speed is constant, no tangential force is needed. So friction is 0 at both B and D. At point C, the road makes 45 degrees with the horizontal. The tangential component of gravity along the road is mg sin 45 degrees. For constant speed, friction must balance this. So friction at C equals 1000 times root 2 over 2, which is 500 root 2, approximately 707 newtons. Part C. Just before crossing C, the cycle is on the convex arc. At point C, the road makes 45 degrees with the horizontal. The radial component of gravity is mg cos 45 degrees. On the convex side, mg cos theta minus n provides the centripetal force. So n equals mg cos 45 minus mv squared over r, that is approximately 707 minus 25, equal to 682 newtons. Just after crossing C, the cycle enters the concave arc. Now n minus mg cos 45 provides the centripetal force. So n equals mg cos 45 plus mv squared over r, that is 707 plus 25, equal to 732 newtons. Notice the normal force jumps from 682 to 732 as the cycle crosses C. Part D. The minimum friction coefficient. Friction is only needed where the road is inclined, not at the horizontal points B and D. The worst case is at point C on the convex side, where friction demand is highest and the normal force is lowest. Mu minimum equals friction divided by normal force. That is mg sin 45 divided by mg cos 45 minus mv squared over r. Plugging in the values, This is 707 divided by 682, which gives approximately 1.04. Here is the complete answer summary. Part A. Normal force at B is 975 newtons, and at D is 1025 newtons. Part B. Friction at B is 0, at D is 0, and at C is approximately 707 newtons. Part C. Normal force just before C is 682 newtons, and just after C is 732 newtons. Part D. The minimum friction coefficient is approximately 1.04. Exam tips. First, on convex surfaces the normal force is less than mg, and on concave surfaces it is more than mg. Remember, a convex surface pushes you off, while a concave surface holds you in. Second, at inclined points on a curved track, always resolve gravity into radial and tangential components. Friction must balance the tangential component for constant speed. Third, to find the minimum friction coefficient, identify the point where the ratio of friction to normal force is maximum. This is typically where normal force is smallest and friction demand is largest. Like and subscribe for more circular motion solutions at MAGPIEHUB.